The brain is the most complex organ in the human body. In the words of Emerson Pugh Lyle Watson, if the human brain was so simple that we could understand it, we would be so simple that we couldn't. Scientists have, until now, only been able to study brain activity in static conditions. Technologies such as MRI and PET, while exciting, limit our ability to understand how the brain processes dynamic everyday situations and how we react in real time. Let us look at a situation where an elderly person is in a supermarket. While pushing the cart, they are simultaneously checking out all the items on the shelves, trying to recall the shopping list and the latest offers. This is called dual or multitasking. In such situations, we simultaneously manage various tasks for which we recruit different resources of the brain. We need our cognitive functions, such as spatial orientation and navigation, working memory, visual attention, as well as postural control while walking.
This situation might seem simple and automatic for young and healthy people. However, the aging process by depleting our neural resources amplifies the so-called cognitive motor interference, which can lead to unwanted situations such as a person tripping or even falling. Until recently, it was impossible to observe brain dynamics during movement. However, the Mobi approach makes this possible, allowing us to monitor brain dynamics simultaneously with biomechanical parameters of human movement. This means that we can now measure what is going on in your brain while you are walking, running, or doing other types of physical and mental exercise.
So the Mobi approach was born from the idea that the human brain evolved to optimize the outcome of our behavior. And active behavior is very important for cognition, as the movement itself generates a lot of sensory input that is necessary to reach a cognitive goal. For example, if I turn around in the city, I get vestibular information, I get proprioception that is necessary to reach my cognitive goal. In other words, motor and cognitive functions work in synergy, and it is important that we investigate them in a co-dependent rather than a separated fashion. And using the Mobi approach, we can finally detach from a sterile, static laboratory setting and let people move freely while we investigate the natural brain dynamics. And this is exciting as it brings new opportunities which can be applied to different target groups such as healthy adults as well as those with certain diseases.
Parkinson's disease is the second neurodegenerative disorder after dementia. The Parkinson's disease is characterized by bradykinesia, tremor, instability, and occasionally cognitive defects. We have particular diagnostic tools to define the diagnosis, like TAT scan, PET, and neurological examination. We have pharmacological drugs, but the not pharmacological treatment is extremely important to manage the patient.
To better understand these challenges and develop protocols that lead to a higher quality of life for all healthy adults and Parkinson's disease patients, we need a strong multidisciplinary approach and the cutting-edge technology. And that's exactly what we are doing through TwinBrain, a project funded by the Horizon 2020 program. TwinBrain brings together research teams from Slovenia, Germany, Switzerland and Italy to strengthen scientific and technological capacities in the field of neuroscience of movement. We have developed a laboratory that takes on an important role of knowledge transfer of TwinBrain research and becomes a point where science meets practice.
We established the Slovenian Mobile Body Imaging Laboratory in the summer of 2021. After systematic testing of individual devices and technologies, we can now see what they all together can do in real-time settings. We're using the fully mobile high-density EEG, high-density EMG and the whole-body kinematics streamed over wireless protocols. We are recording electrical activity of the brain in connection with the firing patterns of individual motor units. In parallel, the 3D avatar reproduces the exact position of the body in real time. For instance, we can link a sensory, cognitive or motor event with a specific brain response. For an outside observer, both healthy adult and a Parkinson's disease patient can react in a similar manner, but the brain of Parkinson's disease patient must work harder to successfully achieve the goal. In our measurement protocols, we collect large amounts of data through multiple data streams that help us better understand the crosstalk between muscles and the brain. This enables us to map very precisely how the brain controls movement and the related cognitive processes. With this technology, we can distinguish the brain dynamics of a healthy individual in comparison to a Parkinson's disease patient.
In order to look into the brain at work during real-life activities such as walking, we need a brain imaging device that fulfills two basic requirements. First, it has to be mobile and robust to artifacts, and second, it has to have high temporal resolution to follow the brain dynamics during continuous motion. The EEG, in fact, is the only method that fulfills these two requirements. Thanks to high number of recording electrodes and new data analysis methods that we developed, EEG now allows to monitor neural activity dynamically with very high temporal and precise spatial resolution during motion. Even activity in deep structures in the brain, such as the thalamus, can be seen with high-density EEG, as we have recently demonstrated with simultaneous depth and scalp recordings in patients. Concerning the future in helping patients with neuropsychiatric deficits is digital health and personalized medicine. With mobile systems as we developed in the TwinBrain project, we paved the way towards the possibility to monitor behavior and cognition in the patient's daily life and provide personalized early diagnosis of brain dysfunctions.
What we find today could serve as a basis for future generation of researchers who will continue looking for ways to improve our quality of life. The TwinBrain project relies heavily on knowledge and best practice transfer by organizing summer schools, workshops, roundtables and visits of internationally acclaimed experts. Soon we may unravel the interconnected processes in our brain as we search for that one missing item on the shopping list. The TwinBrain project represents the next step in the field of brain research, contributing to better understanding of the most complex organ in the human body.